Okay. Um, so this is the last section that we need to cover before we review and take the test on Friday. It's on mathematical modeling, which usually means we're going to have some story problems to go over. But these aren't too terribly bad. Um, Honestly, I've taught out of lots of different books, and this topic isn't in every book, but it's a really good topic. It's a good application of math, and it's also a good way to model things that really happen in real life, and we'll look at some of those things. Okay? So it starts off and it says, when two variables are related, we can often find an equation that relates their relationship. Okay, really that's a lot of what math is. We've got things that change here that affect other things that are changing, and if we can find some relationship, we can make some predictions. Okay? Really important to be able to do that. If you were in business, you'd want to know how your costs or your customer acquisitions or different things like that affect your bottom line, and you'd want to be able to change those. Okay? So one of the easiest ways that we can relate these is when one variable is what we call proportional to another variable. Okay? So as one changes, there's some direct correlation in some sort of way with how another variable changes, or in some cases, how a couple of other variables change. Okay? So there are a few common types of proportional variations. So the first one is called direct variation. Okay? And we'll cover that one, and that's a very common and useful one. The next one is called inverse variation, and I remember learning this when I was probably your age, and for some reason I thought of this as direct and indirect variation. It just made more sense in my head, but we'll talk about why one's called direct and the other one's called inverse, and then the other one is called joint variation. Okay? Each of these has a specific form that we can put in, and there are lots of different ways where we can describe this relationship, because sometimes we'll get a word description of what's going on. Sometimes we'll get an equation description of what's going on. Sometimes we get a graphical description. And what we're going to start off with here is kind of a word description. So this is direct variation, and this is how it can be stated. Y varies directly as x. Or we could say y is directly proportional to x. Or we can say this. We can say it in an equation form. We can say y equals kx as long as k is some non-zero constant. And we have a name for that constant. That constant is called the constant of variation. Okay? Or sometimes we'll call it the constant of proportionality. Okay? And sometimes we'll just call it the constant. Okay? What's the constant in this variation equation? Okay, so we're actually going to go through and we'll look at some real life situations. We'll actually look at some data that maybe somebody collected in some classical physics experiment or something like that. And we'll see how these things might come up and how mathematicians might develop something like this. But let's start off with a fairly simple example. And you might need your calculator for this. Totally okay. We're not going to be doing a bunch of graphing, but it might help with some of the little bits of arithmetic. If we can figure out what it is without a calculator, we certainly ought to do that. And we always ought to have some guess as to what number our calculator is going to spit out once we get that. Okay? So example 1 starts off with a statement, and it says, sales tax varies directly as the amount of purchase. Sales tax varies directly as the amount of purchase. So the sales tax is going to be determined directly from the amount of the purchase. Okay? If the tax is $17.30 on a $200 purchase, it says find the constant of variation. Well, in order to solve this, we've got to have some sort of mathematical model. So let's think about this for just a second. Sales tax varies directly as the amount of purchase. Notice that that uses the same type of vocabulary and the same type of structure as this statement right here on number 1. Y varies directly as x. Well, if y varies directly as x, then that equation for direct variation would be y equals kx. Okay? In this case, we've got sales tax directly related to the purchase price. Okay? And remember, when we've got a story problem, it would be a good idea to choose variables that represent the things in the problem. Okay? So let's not always stick with x and y, which you could do if you wanted to. Okay? So let's do this. Let's say t for tax. And let's use P for purchase. And then let's read this equation again a little bit more simply. T varies directly as P. T varies directly as P. And the way I like to think of this, the way I made sense of this when I was a kid, is these are related directly across the equal sign. Directly across the equal sign. So it was T on one side and a KP on the other. T stands for tax, K stands for purchase price. Okay? So we've got this piece of information. The tax is $17.30 on a $200 purchase. So this right here is an example of tax, or an instance where we were charged tax for this particular purchase price. So what can I do with those two things to help figure out this problem? What is it? Yeah, substitute them in, just plug them in, right? So let's do this. $17.30 should be equal to K times 200. And if you want to figure out what K is, divide both sides by 200, okay? Now, let's see, I'm decent with numbers, but not that good with numbers. Or could we be? Could we take this and maybe we could move the decimal over two places, so we're just taking 0.173 divided by 2? Wouldn't that give you the same answer? It's a lot easier than dividing by 200, right? So, and then we could think of this as 17.3 divided by 2. Okay, if you need a calculator, go ahead and grab one. What is that answer? What is it? 0.0865. 0.0865. Okay? So in other words, that's the tax rate. Okay, and if we thought of that as a percentage, that's 8.65%. Okay? But this right here is the constant of variation. That's the constant of proportionality. So the next thing it says is write a mathematical model for this. Well, our mathematical model would be this thing right here, except for now we know what K is. So we're going to write T equals, or the tax equals, 0.0865 times P. And once I have that, I can answer any question you want. So for example, if I made a $20 purchase, how much would the tax be? Well, the tax on a $20 purchase would be directly proportional. Okay, so this is going to be 0.065 times 20. So what is 0.0865 times 20? $1.73. Okay, $1.73. So on a $20 purchase, it's only $1.73. Okay. What about on a $1,000 purchase? 0.0865 times 1,000. So what's the tax on that $1,000 purchase price? $86.50, right? Okay. Is this a high tax rate? Does anybody know what the tax rate is in Utah? Raymond? What is it? Yeah, it's around 6. Okay, depends on what city you live in, because sometimes cities have sales tax and stuff like that. It's usually around 6.85. Okay, so it's a little bit less than 7%. Okay, are there states that don't have sales tax? There are. Anybody lived in one? What's that? Oregon does not have sales tax. Okay, if you go to Washington, I think Washington might be 10% or something like that. Okay. So 6%, 7% in Utah is probably around average. Some places it's 10%, some places it's 0. Okay, so it just varies. Okay, now take a look at what we've got here. We've got some information. We have 3 different instances. We've got a purchase price of $200. We paid $17 in tax. Purchase price of $20. We paid $1.73 in tax. And $1,000. We paid $86.50. Okay. This is the nature of direct variation. Let me put these in order. $20, $1.73. $200, $17.30. $1,000, $86.50. What do you notice about the way these two vary? As the purchase price goes up, what happens to the tax? Okay. As the purchase price goes up, the tax goes up. They vary together. They get larger and smaller together. They do the same thing, okay? As x gets bigger, y gets bigger. And as x gets smaller, y gets smaller. That's what we mean by direct variation, okay? So we'll say as x gets bigger, y gets bigger. And the same thing, as x gets smaller, x gets smaller. And what we mean is in size. So in other words, they do the same thing. Get bigger and smaller together by some constant of proportionality. Brandon. Okay, excellent question. What if we graphed something like this? Okay, so let's take a look at this right here. Okay, and I could represent it with y's and x. I'd have to say y represents tax. I'd want to kind of declare the variables, and I'd want to say that this represents the purchase price. Or I could just go through and I could label this as the p-axis and the t-axis if I wanted to. So take a look at this. This would be y equals 0.0865 times x. So I'll use x's and y's. Okay. What would this be if I graphed it? Brandon was right. What shape is this? It's a line. Okay. Where does it cross the y-axis? What's its y-intercept? 0. Okay. So stop and think about that. Okay. They both do the same thing. They get bigger and smaller together. So if this was 0, 0 times whatever this constant is would be 0. Okay? So they're always going to go through 0, 0. And then this one's going to get bigger the bigger the purchase price is. Okay? So we're not going to have two different lines here. We just have the larger the purchase price, the larger the tax would be. Does that make sense? Okay, good question. Anything else there? Okay, let's take a look at a couple of other problems. It says, assume y is directly proportional to x. Use the value of y and x to find a linear model that relates x and y. It's literally this simple. When you see that statement that it is directly proportional, so we're going to have y equals kx directly across the equal sign. Take these numbers, plug them in. So this would be 14 equals k times 2. So what's k got to be? K's got to be 7. Your answer is y equals 7 times x. Just for the heck of it. That's a drastically different constant of variation. But if I were to graph that, if this is a slope of 0.0865, a slope of 7 would be much, much steeper. It would grow faster, but they would still do the same thing. They would get bigger and smaller together. Okay, let's take a look at this one right here. Again, y is directly proportional to x, so this would be y equals kx. We get out a -6 when we put in a 20. So that means k would be -6 over 20, or we could write that as -3/10. So our model would be -3/10 for k, and that would be it right here. What would this look like if we graphed it? Any ideas? Raymond? What's that? It would be a shallow line, but it would have a negative slope, so it would go down like this. But again, the bigger x got, okay, the larger y would get in the negative direction. So it's possible to have a negative constant of variation, okay, but they still get bigger and smaller together. Whether they're negative or positive, we're not necessarily concerned with that, okay, although that would be part of the answer, okay. When we talk about them directly varying, okay, the size of the numbers get bigger and smaller together, okay? Sven? Okay, so there's a problem on your assignment. I think 22 is actually on your assignment. If it's not, you've got one just like it, okay? So this happens in the real world. It says the simple interest on an investment is directly proportional to the amount of the investment, okay? By investing $5,000 in a municipal bond, so a very safe investment, okay, you obtain an interest payment of $187.50 after the first year. Find a mathematical model that gives the interest, I, so they're telling you what variables they want you to use, for this municipal bond after 1 year in terms of the amount invested, P. So this I stands for interest. Does anybody know why they chose P to be the amount of money we put in the bond? Okay, the money that you put in an account, okay, that you loan to somebody or that you take out a loan for is called the principal. It's just a fancy name that means the amount of the loan or the amount of the investment, okay? So the interest is directly proportional to the amount of the investment. So the interest is directly proportional to P. I equals K times P. I'm not going to finish this off, but the interest amount was $187.50. We don't know what the constant of proportionality is, but we do know how much was invested, 500. Okay? And it says find a mathematical model. So find out what K is, and then rewrite I equals whatever that number is times P, and that's it. That's all you have to do. You're finding a formula for this variation, not necessarily finding, any specific answers with that. Any questions there? Okay, you can finish that, right? Okay, so let's take a look at another example. This example is from physics. Anybody had some introductory physics? Anybody heard of Hooke's law? You guys heard of Hooke's law? Okay. So here's how this works, and this should kind of make sense because everybody's got some experience pushing or pulling against bungees or something like that. I know I do that in my spare time. Okay, it says so. This is Hooke's law for springs, and it's on 27 through 30 of your assignment. This law states that the distance a spring is stretched or compressed varies directly as the force on the spring. So if you apply a force to a spring or a bungee or something like that, if you pull it, the harder you pull, the further it goes. The more you push, the more it's compressed. Right? Doesn't that stand to reason? Isn't that what direct variation means? Okay? The bigger the force, the larger the distance you'll be able to pull it. Okay? See how they vary directly? So let's declare some variables. So let's say F is the force. And let's say x is the distance. Now, I could use d for distance. That would be fine, okay? But it's a little more conventional to use x for that distance, okay? So it says, write a sentence that describes what this means that the average person could understand, okay? Well, if you were listening, I just gave you a couple ways that you could say that, okay? So write something down, and then I'm going to ask for some people to share that. If you were to describe what Hooke's law means, how it works to a regular person, maybe didn't have a huge science background or something like that, how would you explain to them what this direct variation means? Just a quick sentence or two. In a second, I'll ask for volunteers. If I don't get any volunteers, then I'll just start calling names. Okay, anybody want to volunteer their answer? What does this mean? How would you explain Hooke's law to the average Joe? Brandon. Okay, the harder, say that again. Okay, so the harder you pull, so if we're pulling, the longer it gets, and vice versa, right? Okay, so if we were pushing, the shorter it would get. Okay, anybody else? Or are they all some variation of that? Okay, pretty close, right? I mean, that would make sense to most people. Okay, then it says, write a mathematical model for this variation. So if I've declared F to be the force and X to be the distance, and these vary directly, F equals Kx. There's your mathematical model. Now, what would you need to find K? What would we have to have in order to figure out what K is? And is K the same for every single spring? So let's tackle those in the opposite order. Is K exactly the same for every single spring? Nope. You've got springs on your car that are huge, really thick metal, okay? Okay, those coils might be made up of steel rods that are 1/2 inch thick in diameter, really thick. And then you've got, pull a pen apart, and you've got that little spring in the pen. That's a spring, okay? But that's really easy to compress and stretch. In fact, you can stretch it to the point that it doesn't spring back anymore, right? Okay? So K is different for each one. So what you'd need is some information about that spring. You'd need to know, hey, if I apply a force of 10 pounds, here's how far it stretches, okay? So make sure as you're doing those problems, you understand those, okay? That would be a really good, nice application for this type of variation, okay? Any questions? Okay, so the next two we're going to go through fairly quickly. The next one is called inverse variation, and we can say y varies inversely spell this correctly. Inversely is y, or y is inversely proportional, there's that word again, inversely proportional to x. Okay, or we could just write it as a sentence, a numerical sentence, a mathematical sentence that says y equals k over x. Okay, now again, this is called inverse variation. In my mind, I always think of it as indirect variation because y varies directly or indirectly. It's not directly across the equal sign. We put the x down below. That x needs to go in the denominator. Okay? All right, any questions there? Okay, so there are the statements. That right there is the mathematical format for what we're going to do. So if you flip the page over, most of you are going to take the ACT for the first time in the next year or so. Okay, if you're a junior or a senior, you've probably already taken it once, and you'll be taking it again here soon. Okay, a lot of times on the science portion of the ACT, they'll ask you questions, but they won't give you a huge amount of background. You'll read some passage, and then they'll see if you can understand it just from the context. Okay, whether you've got background in trigonometry or wave functions and different things like that, we can still understand this because this just gives us an indirect or inverse variation statement. The frequency of a wave is indirectly proportional to the period. The frequency of a wave is indirectly proportional to the period. Well, let's see. If we used F for frequency and P for period, then we'd have the frequency equals, so F in this case stands for frequency, not force. If it's inversely proportional, I'd have a K on the top and I'd have a P on the bottom. Here's my mathematical model for this statement right here, but then it gives me some information. It says the frequency is 1/7 when the period is 7. Find the constant of variation. We want to figure out what K is. So this is F and this is P. Let's plug them in. So 1/7 equals K over 7. This is pretty easy because what's K? K's got to be 1. Okay? So here is our model. F equals 1 over P. F equals 1 over P. We figured out what K is. Now we can write an exact model, or an exact mathematical model for this type of inverse variation. So let's figure these out. It says find the frequency if the period is 1/60th, a tiny little number, 1/60th. Okay? So the frequency would be 1 over, what's the period again? 1/60th. Okay? This has a name. Does anybody remember what it is? We reviewed this in chapter P. Complex fraction. Do we ever divide by a fraction? Nope. I'm going to flip this over and I'm going to multiply. So that's going to be 60 over 1. So what is the frequency? Whoops. Frequency is 60. Okay? So if the period is 1/60th, the frequency is 60. What if the period is 200? Let's do that problem. So the frequency would be 1 over, period is 200. Is there any work to do here? Nope. There's the frequency. So if the period is 1/60th, if the period is this tiny little number, the frequency is 60. If the period is this big number right here, the frequency is this number right here, 1/200. Okay, so let me put these in order. If the frequency is if the period is 1/60th, the frequency is 60. If the period is 7, the period is the frequency is 1/7. And if the period is 200, the frequency is 1/200. Okay, so let's write this. Period, frequency. Let's see. Smallest period was 1/60th. Frequency was 60. Next smallest period, 7. Frequency is 1/7. Whoops, 1/7. And if the period is 200, the frequency is 1/200. Okay, what do you notice about these? And can you see why they call this inverse variation? Okay, I see some shaking heads. Somebody want to tell me what you notice? How do they change with respect to each other? Okay, when we had direct variation, they both did the same thing. As one got big, the other one got big. As one got small, the other one got small. Hop. Okay, so as x gets big, y gets small. And vice versa. As x gets small, if we look at it the other way, okay, as this original variable gets smaller, okay, that one gets big. So in other words, they do the opposite. As one gets big, the other one gets small. So can you see why they'd call this inverse variation? Okay. All right. Any questions there? Okay. You don't have a ton of problems to do in this homework set. The more important of these, I mean, we could dwell on this and we could do tons and tons of different problems. The most important one would be direct variation, but we should get a little bit of a flavor for inverse and also what's called joint variation and nth power variation. So let's fill this out right here. So joint variation means that one of the variables is determined by two or more other variables. So joint, it's jointly determined by a couple of other variables. Okay, and then nth power variation is kind of just like it sounds. It means the value of the variable is determined by a power of one or more other variables. And sometimes we do a bit of a mix of these. Okay? So you've got several problems on your assignment where there's not really a lot of math. It's just, do you understand these type of variations and can translate from an English sentence to a mathematical equation, or from a mathematical equation into an English sentence? So let's take a look at this one right here. This says b, capital B, varies directly as the square of y. So let's start with b. Varies directly, or is directly proportional. What do I need to put next? A k. As the square of y. What goes over here? Y squared, directly across the equal sign. Varies directly as the square of y. Okay, that's an nth power variation. Okay. Next one. Y varies inversely as x and directly as z cubed and w squared. Y varies inversely, so I'm going to have a k on the top, and what goes on the bottom? An x. and at the same time directly as z cubed and w squared. Where do I put those? Directly across the equal sign. So this is going to be z cubed, w squared. Okay? And that's it. You have problems where you don't have to do anything with those. All you have to do is come up with a mathematical model for them, and you don't have to find what the constant of variation is. Okay? If given enough information, we could do that. Okay? But luckily, all you've got to do is just write down what that mathematical equation would be. And then you've got some that say, translate the following equation into a sentence that describes the variation. So, V equals pi r squared h. Hopefully that rings a bell. Does anybody know what that is? What is it? Volume of a cylinder. Volume of a cylinder. Okay? Volume of a can. Okay? Oops. Make that look right. Okay? Volume of a circular cylinder. Okay? So, we'd say V varies how? Directly as okay. Do I need to put the pi in there? Is pi a variable or is it a constant of variation? It's the constant of variation. It takes the place of the k. Okay. Did we ever mention what k was in these sentences? Nope, you don't need to worry about that. It's only the variables that we're interested in describing the direct or inverse variation. So varies directly as r squared and h. Next one. P varies. How does it vary? Okay. Inversely as what? W cubed. Is that it? P, W cubed down on the bottom. What's on the top? An N. So, and directly as N. Okay, you write the last one. R varies. And I'm going to start off with directly. Directly as D and inversely as T. Okay? Easy enough? Okay. Now, you have some problems that are just like that. Okay? They'll give you a formula, and all you have to do is describe it. Again, take note, we didn't need the pi, because that's a constant, not a variable. And this number right here is a 4, or if we looked at this another way, this would be 1/4 n over w cubed. So that 1/4 would be the constant of variation there. Okay? All right. So the last little bit, this is just kind of an open-ended problem. And for those of you that have had physics before, or you watch a lot of those programs on PBS and stuff like that, this is actually kind of an interesting thing. Okay? When Galileo was trying to figure out how gravity worked, they used inclined planes, and they rolled balls down these planes all the time. So they'd have big, long ramps. They'd put a ball on it, and it would have kind of a little trough to keep the ball from rolling off. They'd put it on there, and they'd try and time, if at 1 second, how far does it go? At 2 seconds, how far does it go? At 3 seconds, and they'd mark those off, and they studied this, and studied this, and studied this, and studied this, and figured out, hey, this is how we could figure out the nature of motion, or formulas that would describe how things are affected by gravity. Okay? Now, I made this problem up, okay, so that the numbers would work out fairly well, but let's think about this for just a second. So here's the situation. Imagine you're in a lab and you're taking these measurements. We've got two particular measurements here. We drop this ball and we start a stopwatch, okay? And we've got marks on the ramp that show in feet, okay, in this particular case, how far the ball is going to go, okay? So at 1 second we mark it, at 2 seconds we mark it, and the data that we've got was collected at 2 seconds. After 2 seconds, the ball had rolled down the ramp 3 feet. After 4 seconds, the ball had rolled down the ramp 12 feet. So in the first 2 seconds, it covered 3 feet. In the first 2 seconds, it covered 3 feet. In the next 2 seconds, it covered another 9 feet. Equal time intervals, but what was happening to the ball? Faster and faster and faster, okay? If I plug in a 2, I get out a 3. If I plug in a 4, I get out a 12. Okay, now, what type of variation would we be talking here? Would we be talking some sort of direct variation, or would we be talking about some sort of inverse variation? And why? It's one of those. Can you say which one it is? And can you say why it's got to be direct or why it's got to be inverse variation? Think about the examples that we've already gone over. Cameron's got an answer. Anybody else? Okay, got 3 or 4 other people with an answer. Think about that for just a second. How are these changing? Because if you just think about it, you can tell for sure which one it's got to be. Some sort of direct or some sort of inverse variation. Cameron, which is it? Direct. Why is it direct? Very good. Okay, that's exactly right. Our description that we used earlier to describe in just layman terms what direct variation means, they'll directly vary is if as one gets bigger, the other one gets bigger. As the time gets bigger, as the time period grows, so does the distance the ball was able to cover. Okay? So this is some sort of direct variation. So the simplest model for direct variation would be this. Okay? And let's use D for distance. So we'll declare some variables here. So distance. And let's use T for time. So if we did something like this, D equals KT. We have this piece of information right here, right? So let's plug that in. The distance is 3 feet when the time is 2. So our guess is K equals, careful, 3/2, right? K equals 3/2, correct? Okay. So this is our guess. Okay, and this is an oversimplified version of what they actually did. They collected some data and then they said, well, we're going to guess that the distance is directly proportional to the time. That was their first guess. And their guess was that on this particular ramp, which probably is fairly shallow, not very steep. I mean, if we did a really steep ramp, it would go down really fast. Okay, cover a lot of feet very quickly. Okay. So probably a gently sloping ramp. Okay, here's their first guess. The question is, does this work? And by does this work, we mean, can you use this to predict other answers? Because if we got it right, we should be able to conduct this experiment and say, you know what, if 4 seconds goes by, I should know what the answer is. Okay, what if we plug in a 4? What do we get? Cancel these, that's a 2, so we get 6. Is that the right answer? It's not. Okay? Is this the right model? Can't be the right model. But it's got to vary directly, doesn't it? As one gets big, the other one gets bigger also. Okay? Anybody want to take a guess at another model? It's got to be some sort of direct variation. D equals K. It's got to have something to do with time. Cameron's got his hand up again. I suspect Cameron's been watching a lot of YouTube videos on particle motion or falling bodies or something like that. Cameron's shaking his head. Cameron's just smart. Okay, Cameron's got a good guess for us. Let's hear it. T has an exponent. Cameron is exactly right, okay? This is nth power variation. This is nth power variation, okay? The distance is directly proportional to some power of t. And after lots of experimenting, they found the correct power. Anybody want to take a guess? What would be the next easiest power in addition to 1 that we used right there? Let's use a 2, okay? So let's do d equals kt squared, directly proportional to the square of the time. Directly proportional to the square of the time. So let's see what it would be here. Let's start off the same way. Let's find our constant of proportionality. Let's figure out what k would have to be. So this would be 3 feet in 2 seconds. So let's square the time. This would tell us that k is equal to 3/4. For this particular ramp, for the steepness of this ramp, we're hoping that we can make a prediction using this model. D equals 3/4 t squared. The distance that it travels down the ramp is directly proportional to the square of the time. Now, how do we know if this works? Plug in another time. We took one more measurement, okay? We got 4, so this is going to be 3/4, 4 squared. I'm going to cancel one of these with one of those and multiply those together, and I get a distance of 12 feet. Did this work? Okay. So do we think this is right? Here's our guess. Is that right? Okay. Let's say you were going to get paid $100,000 if you could get the right model for this ramp. Cameron's smiling right now. Okay? This is the right idea. If you had to guarantee somebody, you only got one shot at giving them your answer, and they would pay you $100,000 if you got it right. Have we done enough work to make sure that this is the correct model for this ramp? No. What else would we want to do? Just because it got one answer right, 2 answers right, is that enough? Nope, we'd probably want to check several more of them, right? So we might want to go back and say, hey, you only gave me 2 pieces of data, 2 time measurements. Can you tell me how far it goes down the ramp at 1 second? And if it matches up, that's more evidence. Should match up at 3 seconds, 5 seconds, and so forth. If it matched up for, say, 10 seconds, do you think that would be pretty darn good evidence? Would you feel confident in submitting your answer? Yeah. And the cool part about this is exactly what they did. And then once they figured it out for one ramp, they went to maybe a more shallow ramp and figured out that constant of proportionality. Did a steeper ramp, figured out that constant of proportionality. And guess what? Every single time, it was always this model. The distance was always proportional to the square of the time that you let the ball roll down the ramp. Okay? And that leads to eventually, let's get rid of the ramp and let's do this. Let's just drop something. Because all a ramp does is slow down the dropping, right? It's really hard to measure how far something dropped. I mean, imagine several hundred years ago trying to keep track of how fast something dropped or how far it had dropped in 1 second. Okay? Would you really be able to do that? No photography, no video? Be kind of tough, right? So those ramps slowed down the dropping so that they could take accurate measurements and make better predictions. Okay? Any questions? All right. There aren't that many problems from 8.1. Again, please come tomorrow. 1.7 is due. Please be done with 8.1 and do as much of the review as you possibly can. So tomorrow is just questions. Review, look at the notes, look at the homework.